Oops, let me switch this really quick. Okay, yep. So my name is Alex. I'm an application engineer at Materialize. I've been with the company for 6.5 years now. My undergrad is from Michigan Tech in biomedical engineering, and then I did my master's at Wayne State, also in biomedical engineering. Right now, yeah, I'm an application engineer. I support academics, and then I also support our hospital customers, so groups that are using the software for research applications, but also for clinical cases, which I'll get into some of those as we go on. We do have another, on the medical side, we do have another team that works directly with medical device companies. So those companies are using the software for device development and things, so patient-specific device development. So most of the major companies that are doing device development and production and selling those devices, a lot of them are using our software. So I'll start with it's a pretty high level presentation about what we do, what our software does, different applications that you might see, and then I'll jump over to the software and give a fairly quick overview of the segmentation process, and then some of the prep that might be done for, say, going to an FEA solver. Some groups are going to CFD. There's a lot of different applications, so I didn't want to get too technical because what I show might not be exactly what needs to be done. Um, and I'm going to do it on a basic example because, yeah, I saw the micro CT of the fallopian tube, and I don't think my laptop would survive a presentation with that data. It's a lot of data. So I picked something easier, but I'll get started. So Materialize, who are we? We are a global company. We kind of have our feet in a lot of different applications. So we have software on more of the industrial side, so supporting automotive, aerospace, things like that. In the healthcare industry, we have software for that as well. And then we also do have a lot of printers throughout the world that are producing parts for multiple different applications. So we have 27 offices right now in 20 different countries, and I don't know how, I feel like it keeps growing, so I don't know how accurate the 2,000 employees is. But we're a global company. Our headquarters is based in Leuven in Belgium, but I'm based in Plymouth, right outside of Detroit in Michigan. So where do we fit with a lot of these applications? So we kind of are a broad, like as I mentioned, a broad company with a lot of different applications. So on the software side, we have programs like Materialize Magics or Streamix that are helping users prep models for 3D printing or basically tracking their workflow. So as parts are getting put on builds for printing, being able to maintain that, track things like, say, if you're using a powder bed printer, how much powder was used, things like that. And then again, we have more of a service bureau, so that middle Materialized manufacturing. So we have, yeah, a large number of printers around the world printing parts for healthcare, also aerospace, automotive, really anything you can think of. We have eyeglass division. So that's probably that's the biggest right now is the manufacturing, and then where I'm at is the medical. So within medical, we have more of our point of care services. So that's like the hospital applications. We have our medical device companies, and then we have our academic groups doing more research. Within academics, we have veterinary as well, so treating animals. We also have a service line within our medical. So we have different clinical services, whether that's for shoulder planning, craniomaxillofacial. So one of our groups actually supported the first face and double hand transplant, as well as a face and eye transplant. So we kind of have our feet everywhere, but I'll be focusing more on the medical side today. So on the medical side, on a yearly basis, we are helping over 50,000 patients using our technology, whether that's a service-based print or using our software in-house. So you can see we up to now, so we've been around for about 35 years. We've produced over 350,000 patient-specific models, guides, and implants. And then in-house, so using our software has been used to analyze 50 million patient scans. On more of the academic side, so like where this software might fit in on your end, um, people are using our software to do more patient-specific research. So taking all of the CT, MRI data, 3D echo, converting that to 3D models to then accelerate their research. So we have 11,000 peer-reviewed paper citations. Over 600 research institutes are using our software. And then within a lot of those institutions, they're also using our software as part of their curriculum to teach students how to basically do this image processing. So when they get to the field of, and they're say at a medical device company and they're doing patient-specific device development or anything like that, they're already kind of ahead of other applicants. Oops, I skipped a slide. Okay, so uses of our applications. So you can see on this slide, kind of where on the medical side where we kind of shine. So one of our biggest business units on the medical side is craniomaxillofacial. So taking patient CT scans, converting that to a 3D object, and then with the surgeon, our clinical engineers will plan a case, basically cut all the bones, move them into the position they would like, and then on our side, we will design and print plastic guides, so cutting guides, as well as 3D printed titanium implants and cutting guides. And then we also have different service lines. So our knee business is quite large. So we have an automated workflow to basically plan knee replacements, anatomical models. So a lot of our hospitals are starting to include these anatomic models as part of their patient treatment. So this is just a few applications. I'd say so. I work primarily with a hospital group, so I wanted to cover a little bit of why they are using this technology in-house. So one of the biggest applications they're using is procedural planning. So with this study, they found that 96% of surgeons are basically agree that these 3D models are helping them understand patient's anatomy before going into an operation. So in this specific case, they were looking at congenital heart deformities. So whether that's different chambers are swapped or there's holes between chambers, being able to physically see that before they go into the operating room is always quite beneficial. Um, similar story here, just with a different type of case. So they were looking at spinal cord and tumors and positioning, so they could basically see where that tumor is located relative to other tissues within the body. And then another big reason that people are doing this, are starting to do this in-house in the hospital, is to save time in the OR. So saving time is better for the patient because they're under anesthesia for less time, but it's also better for the hospital because they're in the operating room less, which means cost savings. So that's part of why a lot of these hospitals are taking this on. Another thing that people are doing in the hospital, and we're starting to see it a little bit more on the academic side, is procedural simulation. So designing and printing a model and then placing a device and say running fluid through it to see how the fluid interacts with a device physically before say a procedure, or if it was more of a research application. We were also seeing it for device sizing. So knowing before you go into an OR, what size device you need to use instead of when you get in there trying to figure that out. So you can save time that way. Patient communication is another one. So in this case, there was a cardiac tumor, and they were trying to figure out the best way to approach. They were going to surgically go in and basically burn the tumor out. But they decided after they saw the model that it was actually in a position where that heart was functioning fine, and they didn't need to do any surgical intervention. So lots of different applications more on the hospital side. Now getting into more of the, I'd say, a little bit of clinical, but also more of the research and technical side. So virtual reality, this is becoming more popular. So being able to take this patient-specific anatomy, bringing that into a virtual space to kind of save money on printing, but also allow for different functionality of viewing that you may not get with, say, a 3D print. Hands-on surgical training. So this is becoming very popular in medical schools. So being able to print a certain deformity or a certain common application, and being able to practice that procedure on a printed model instead of on a patient. So this is helping resident training and things like that. We have some groups that are going to the length. So this is Boston Children's Hospital. What they're doing is they're actually patient-specific modeling all of their congenital heart cases. And then for a lot of them, they're actually taking that anatomy into CFD, and then they're basically seeing how that blood's going to flow through. In this case, they were able to design a cuff to help increase the blood flow in a certain area. So a lot of their cases are actually doing CFD analysis directly in the hospital. So they have a whole team of engineers doing this work. Complex surgical guides, so virtually planning cuts, designing the cutting guides, printing these cutting guides can basically decrease the time in the OR, but also increase basically the intake of that graft in a certain situation. Veterinary medicine, this one's becoming a little bit more popular. There's a lot of less regulations, so I think they're kind of pushing the boundaries with what's actually possible. They're not dealing with humans, so yeah, there's no FDA breathing down their neck. So they're doing very complex cases a lot of the time, or they're just doing research to kind of see how they can advance their field. On the medical device company side, physical model creation is something that's quite popular. So being able to say, develop a benchtop model to, flow, say, physically feed fluid through this model and see how it's interacting. So that's a big thing on the medical device side. Virtual implantation. So this video should start. So this is something that can be done using our software to get to that anatomical model, and then seeing how say a stent would be deployed. This is outside of our software, but that the anatomical structure was created in our software. FEA, so I'll touch on this a little bit, but we have a lot of more research groups studying biomechanics of different structures. So in this case, they're looking at how the bone may interact with an implant that has been implanted in the patient. We have different export options, so depending on what solver you're going to be looking at, we have different export options, and then we can assign material properties based on so basically the intensity values of the CT or MRI scan as well. This is a newer area that I'm seeing, not necessarily in my territory, but more on the medical device side. So being able to take a population of patients, develop a statistical shape model, and then start to design their medical devices off of a population-based study instead of individual patients. So basically taking a wide range of structures, creating what's considered an average, and then trying to basically design their device based on this. And then we're also seeing a lot of groups getting into scripting. So a lot of this stuff can take a decent amount of time. So being able to use Python to access all the APIs within our software and basically script everything. We're seeing groups that are also developing their own AI algorithms for segmentation using our scripting as well. So that's what I have for the presentation. Before I get to the software, are there any questions? I know there's a lot of stuff I just spit out, but
yeah, there is one. So go ahead.
So like when you let's say you start a new project on Mimics for the Materialis, I don't know, I'm sure Mimics is just one of the many ones you have, but if you open a new project, how do you get like a specific, I guess, threshold? Because I see that like, by the way, I'm the one that you were emailing with, that like I got trial Mimics. I'm trying to figure out, I guess, how to superimpose one shape onto another. Because I have uploaded a zip file of DICOM, and it opened, like, you did a great job opening. And then I was able to isolate the outer, like the geometry of the fallopian tube. That was it. And the more accurate the outside is, the outside of the geometry of the actual fallopian tube, the less accurate the lumen is.
Yeah.
Way to like isolate the outer geometry perfectly and then isolate the inner geometry perfectly and then superimpose one on top of the other.
Yeah, so I mean, the easiest way that you might have to do that is, um, yeah, I mean, there are a couple ways you could do it. The easiest, well, probably not. I played around with the data that, and none of it was super easy because my computer was, yeah, struggling. I just have like a normal laptop. Um, but you can, yeah, you can create different masks in the software, with basically different minimum and maximum. So you might be able to, yeah, have a mask specific for the outside, with that, say, wider range that gives you the more accurate external, and then have another one for that internal. And then you should see in the software there's some Boolean operations to where you would be able to combine those two, and get rid of really any overlap. So that could be something to try. Uh,
Cool, and then like, for, you said that you can give values to like material, so like you can basically decide how elastic it is or.
so it's going to be basically a static material because you're looking at a static image. So once you've, say, gone into 3matic, you created the volume mesh. You can bring that back into Mimics and assign the material properties. So Young's modulus, Poisson's ratio, uh, and I'm going to show a little bit of this later. I'm going to just briefly touch on it. But then it basically takes the intensity values from the CT scan, and all the parameters that you set per material, would basically then be assigned to those individual voxels. Um, so I'll briefly touch on that. And then once you export, that material assignment should be included in the export for, say, if you're going to ANSYS or something.
Yeah, I was wondering, what's the format, like the common format that is exported once you're done with the project?
I mean, if you're going to a solver, I mean, I'd say a lot of my academic groups are doing ANSYS, but we have like Abacus, a couple other ones as well. If you're going to, if say you're going to do your meshing, maybe you have a software that can do your volume meshing already, and your surface meshing. Being able to just export like an STL is also an option, but then that kind of limits what you can do on the material assignment, because that's going to require, yeah, to be one of the more FEA exports. And I can show you the exports as well in the software.
And then, oh, sorry, one last thing, like if I'm trying to, because I initially did the isolation of the lumen geometry with 3D slicer,
Hmm.
which was not as detailed. Once it exported, there were a lot of sort of cutoffs where I didn't have, when I isolated it through 3D slicer, there wasn't any like gaps. But when I exported it, there were these huge gaps. That could be because of like the amount of, what is it, faces or facets? They were less when I saved them than what it looked like when I was making it. I guess my question is like, if I did that again with Materialize where I just isolated that lumen, how detailed is the isolation? Because it's a very small sized object, maybe that
Hmm.
it's harder to get a lot of detail and to like, because some of these pieces of aluminum are extremely small where there's probably this very tiny opening.
Hmm.
How deep?
Yes, I mean, so it's going to depend on how you segment and then calculate the 3D object. So if say those smaller structures, if it's too small, when you calculate the part, you may see that, yeah, it may break off. So if that's the case, you may have to kind of, I mean, there's a couple ways we could go in and try and fill that area in. Um, we have some ways to basically connect two regions. So if it does kind of separate that way, we could, I wouldn't say artificially, but we could try and go in and repair that. But it depends on what your segmentation looks like, and how that conversion from the voxel data to a 3D object goes. But yeah, we see that with like vasculature. So the further away, say in the heart, the further you go away, those vessels are getting smaller and smaller. Depending on the operations that you're doing, you might start to break off those ends because they are so small. So some of the parameters that you need to choose, it's going to depend on the resolution of the images plus like, yeah, the actual parameters you're picking in your operation. So whether that's like if you're doing a wrap operation, making sure your smallest detail is small enough that it's going to basically make sure that's covering that structure. But then if you go too small, your data or your part is going to be extremely large. So the more triangles, the larger the part file. Yeah, I can cover a little bit of that as well.
And then actually, do you recommend that so that the computer isn't crashing to do it in segments, I guess, very detailed segments, I guess?
I mean, that's something you can do. I also, when I was working with that, the data that got sent over, um, I found it helpful to not have like the 3D preview on, because it's trying to basically project all of these voxels in space. So turning that off helped a little bit. But yeah, the smaller the section, the better it's going to perform, I would say. Yeah, but with these micro CTs, and I think that data set was like 8 GB or something when I looked at it. Yeah, it's not going to be as fast as a clinical CT where maybe it's a 500 megabyte scan, which is you'll kind of see today. But yeah, doing segments and then kind of combining them might be an option, but then you might run into problems um, creating the 3D model, editing the 3D model, and then I mean that's something that, yeah, I guess you could play with and see how it works, versus say doing the full thing at once.
Yeah.
But performance wise, I think, yeah, doing segments would be better, but it may not help with some of your downstream applications.
The option to code, what is that like mainly, like how does that benefit what you're trying to do?
So like the scripting, so this one. So that's just speeding things up for groups that are doing very similar work over and over. So I have some groups, so like Mayo Clinic, they are doing clinical models for the case for basically they're doing it for every case type, but there are certain case types like like kidneys, that the models they're designing end up being the same thing every single time. So they were able to basically write a Python script that they could just hit go. It will recolor all the parts. It will add lattice to the kidney so you can see inside. It will design the base plate. So it just saves time. That's really more of where the scripting comes in. For like a one-off project, yeah, I'm not gonna tell anybody to script it because it's not saving it. You're gonna spend more time writing the script than you would maybe segmenting. It's for those groups that are doing high quantity workflows.
Yeah. Thank you.
Yep. So I will jump over to the software really quick. So I mentioned before that I'm going to be doing a quite simple application. So I'm just going to be looking at the heart, segmenting the blood out. You could really segment any tissue that you want from a scan. So if I wanted to segment the bone, in this case, I could. But I'm going to look at the blood. I'm going to basically look at the left heart, combine that all into one, and then go through a quick process of refining my surface mesh, creating a volume mesh, bringing it back into Mimics to, say, assign material before export.
So Alex, a question, is this a MRI or it's a X-ray?
This one's a contrast enhanced CT.
Okay.
So you can see the left, well, the left, yeah, I mean, the whole thing is pretty nice. The left side has a little bit more contrast. And I'm going to focus on the left side, but looking at this, it's actually well distributed throughout the whole heart. Typically with the cardiac case, you'll see one side has more contrast than the other, but this one's actually pretty good overall. So what I'll do first is I'm going to use one of our AI segmentations. So we have the CT heart tool. What this is an AI-based algorithm to go through and automatically segment the different chambers of the heart. So I could do the full heart, it takes a little bit longer, and then say I'm not interested in the right side of the heart. I can use this automatic left heart. I'll hit apply. It's going to go through, look at the data, and basically separate out these 3 different sections. And I apologize if you hear a child screaming. They
Yeah,
just got home. They just got home.
that's
But yeah, this is an AI algorithm, so we do have a fair amount of algorithms that we've trained in-house that have been deployed for our customers to use. So our CT Heart is one of them. They tend to be for more of the higher volume applications. So cardiac's one that groups benefit from speeding up the segmentation. We have one that we just came out with for the spine, to basically where you can upload that case to our Mimics viewer platform, request a segmentation, and then it will segment every vertebrae individually. And then you would basically just download that segmentation. So we do have a large profile of those. Are we going to have fallopian tube segmentation? Unfortunately, no. You're the first group that
no
I've
one
worked.
actually is working on this, so that's a challenge that we are
Yeah,
facing. No one
yeah.
is.
So yeah, I think in your case, you're probably going to run into a lot of questions because yeah, I don't have any groups specifically working on fallopian tube. So these questions that are coming my way, I don't always know the
It should
answer
be very
because
similar to the intestine. I don't know. Have you had any group working on the, the large or the small intestine?
it's not as frequent. I just talked to a group in California that is going to be doing more abdominal work. So I'm assuming they're going to get into the intestine segmentation, but um, they haven't really started yet. They were just kind of talking to us about what's possible. But yeah, I haven't worked with anybody doing it. Doesn't mean they're not. Um, and it depends on the imaging as well. If it's high resolution scans where you can clearly see everything, segmentation tends to be a lot easier. If it's a low resolution scan where it's hard to pick out anything. So I have groups that are trying to segment bone from MRI, and that gets quite tricky, especially if they're not using the correct sequencing in their MRI. It gets quite difficult. So a lot of my groups, they ask me how they should scan their patients, and I'm like, you should scan it so you can clearly see what you want to get out of the imaging because that's really the best way to do it. And the data that you sent over was, I mean, it was micro CT, it was quite high resolution. And yeah, it just took a little bit to get. I think I sent you some screenshots.
Yeah.
So I can get a preview. Back to this, so I can get a preview of what that result was. If I'm not happy with it, I could manually go in, place a seed point, and have it run again. But in this case, say I'm happy with this, I'm going to hit OK. And what you'll see is I will get in my list my different chambers. So I'll quickly go through and make some edits here. So maybe for my analysis, I'm not interested in all of these branching vessels. We have tools to quickly go through and get rid of those. So let me just go through and quickly get rid of some of these branching vessels because I'm not going to use them. Certain situations I would, but in this case, I'm not. And it doesn't have to be perfect for this. We have other tools that can still, I left some floating voxels around. I have a tool that can just quickly get rid of some of this here. So say I'm happy with that being my left atrium, the right ventricle or the left ventricle. Again, I'm segmenting blood, so it's quite rough. But what I'll just do a region grow here. So again, I'm showing about the simplest workflow that we could. I just knew with the timing, I wouldn't have a ton of time to do a lot. So then same thing here, I maybe trim these head and neck vessels off. Maybe I'm not interested in the coronaries. And then maybe some of this vasculature. And I do have groups that are quite interested in, say, the coronaries. They'll keep those and maybe they'll fit a center line to that coronary so they can. I've seen some groups, yeah, they'll basically fit a center line to the coronary. They'll use that center line to define a plane that's perpendicular so they can cut the ends so they can say bring it into CFD, like a CFD platform and simulate fluid through those coronaries to see how it's working. So the applications are quite wide, and then let's do reach and grow really quick. So now I'd have these updated, a little bit cleaner segmentations. So if I wanted to see how they looked in the images, I could scroll through, see how those looked. Say I'm happy with these. Right now it's just voxel data. So if I were to zoom in really far, what you would see is this is just a connection, or basically a collection of 3D pixels, so a voxel. In order to really do much with this, we actually need to convert that to a 3D part, or natively within Mimics and 3matic. So I'll show 3matic in a little. It's an STL file. But to do that, I'll just calculate a part, select my 3, hit OK. And then what's nice is once those are calculated, I can toggle on my contours and check to make sure that what I segmented is anatomically accurate. So in this case, yeah, I segmented the blood. I'll clean this up so this contour is smoother. We're not having some of these internal structures, things like that. But that's kind of the most basic workflow for segmentation. Now that I have these structures segmented, what I can do is jump over to 3matic. So Mimics Innovation Suite that I'm showing you today is comprised of 2 different softwares. So Mimics is where we'll do more of the segmentation, and when we get to it, more the material assignment. But 3matic is, I'd say, more of our CAD. It's not necessarily CAD, but it's CAD-like, for post-processing these parts, as well as some of those remeshing tools that you should have access to at the moment with your evaluation. So remeshing the surface, also creating volume meshes and things like that. So that's kind of where I'm jumping now. The nice thing is there's a direct connection between the two. So right now I just have it launching on my other screen. But I just use this export to 3matic. It will basically take those 3 parts, bring them into 3matic, and then I can start my post-processing here. So I will do a quick cleanup of these parts just to make them look and be a little bit cleaner. So right now there's internal shells, there's all sorts of surface issues that might cause problems downstream. Let's go there. So I'm just going to do everything the same. A lot of times, and this is kind of where I mentioned before, if you do have really thin structures, so say you're doing a wrap operation, the smallest detail, that's something you'll want to pay attention to. Basically, that's going to be the resulting triangle on the surface, and that triangle is being used to approximate the shape. So say I was looking at a coronary that's maybe 0.2 millimeters or something, and I'm trying to use a triangle size that's 1 millimeter. You're not going to be able to approximate that curvature. So that's just something that as you work in the software with certain structures, you just kind of become accustomed to. So basically knowing how large these structures are as you're going through is quite helpful. Now that that's done, I'll just smooth out the surface a little bit. And I'm trying to do all 3 of these at the same time, so it does take a little bit of time. And I probably 0.625 millimeters might have been a little bit too small. So you'll probably notice in the software as the number of triangles per part increases, operation time also can increase. So it's not the greatest. If there were certain areas that I wasn't happy with, we do have some local smoothing that I could come in and try and clean this up. But for the purpose of this, I'm not too concerned. So if I wanted to see my triangle size on the surface right now, you can see it's quite small. So this, yeah, it's probably just too small in general. My part size is quite large already. So before I move to more of the remeshing, I'm actually going to fix these STLs. So within 3matic, we have this fixing tool. And what this is going to allow me to do is basically assess each part and see what triangulation issues may be there. So going through and fixing these parts before I say create a volume mesh can be helpful, because any issues that you have in your solver may be caused by this. So I'm just going to go through and quickly fix this. And yeah, so let me do this one. Okay, so there are a couple of issues here, so I'm just going to quickly fix them. So right now there's some floating triangles, so you can see them here that maybe are important, maybe aren't. And I'm just going through and getting rid of them because they would cause issues downstream in this case. So I'm going to say these are all good now. So more on the prep for finite element analysis. We have this remesh menu. What this is going to allow us to do is basically optimize the mesh of all of our parts. Once we have that surface mesh optimized, we can then say create a volume mesh. And then that's kind of where we would bring that back into mimics. I'm going to combine these parts so that I'm just doing it on a single entity. And how you approach this is going to depend on what you're trying to do downstream. So some groups are doing like non-manifold assemblies and then doing their remeshing. That's all. So we have the create non-manifold. It really is going to depend on what you're trying to do downstream. So in this case, maybe I want to do a uniform remesh to where I want every triangle on the surface to be a similar size. So say I want to do a uniform remesh, I'll select let me remove these really quick. I'll select my individual part here. Say I want my target triangle edge to be 2. It might be a little large, but we'll go with that. So if I just hit this uniform remesh, that will basically try and create a new surface with every triangle being 2 millimeters on the edge. We do have other options. So if you need like near a boundary to say have a smaller triangulation than somewhere a little bit further down, that's something we do have. We have a gradient remeshing. We have an adaptive remeshing. So we do have some capabilities there. And I'm already seeing some issues, so that's exciting. Once we've done that, then I might go through and fix some of these issues, but I don't want to mess it up too bad.
May I ask a question?
Yeah.
Yeah. So why we don't see they are not hollow. It seems that they are solid objects, right? So they are not. There's no lumen, for example. We don't see any holes for the blood vessels.
Yeah, so that's kind of just how I segmented this. So in mimics, in this case, I actually segmented the blood, so that's filling the lumen. Yeah, so a lot of my groups, it's with a CT scan, it's going to be quite difficult to actually segment the actual tissues. So I do have some groups, a lot of groups that will segment the blood, and then we do have the ability to basically hollow it out. So if I wanted to hollow this structure and assume a wall thickness, so say I'm assuming a 2 millimeter wall thickness.
Yeah, that's a good trick. So for you, you chose the lumen itself.
Yeah. So in this case, yes, not every situation is the same. But yeah, if you were interested in more of the external structure. So now so I just hollowed it and say I wanted to see inside. So this is what people are doing for their 3D prints. They'll segment the blood, they'll hollow it, they'll cut it open, and then they'll be able to basically see that internal structure. One benefit with the cardiac cases of segmenting the blood is when you do that hollow, yes, your external structure is not going to be anatomically accurate because you're assuming that wall thickness. But the intracardiac, so that internal surface, because it's the same as the outer surface of the blood, that is actually accurate, and that's what a lot of physicians are interested in, is that intracardiac anatomy. You can do, so I've segmented the kidney with a tumor where maybe the external surface is what's important, So you can hollow inwards and then cut it open to where the external structure relative to the tumor is accurate, so that say the surgeon's trying to plan their resection margins, they know that the basically the interaction between the tumor and the external surface of the model is anatomically accurate. So that's just the way I segmented it. That's why it was solid. If you were doing a structure that was hollow on the inside, you would see it that way. That's just, yeah, how I segmented it.
Nice. Okay, thank you.
Yep. So I'm going to undo that hollow. And then we'll see if this fails. I'm just going to quickly create a volume mesh. So creating a volume mesh, some groups aren't doing this. Maybe they have an external program to refine their surface mesh. They have their volume mesh. Maybe they know what softwares they can use to do that. Maybe they find that in our case, these volume meshes we can only create in tetrahedral 4 or tetrahedral 10. So maybe a group's trying to do a hexahedral mesh, and they find limitation there. So maybe then they'll just export the STL here and then bring it into their other program to do more of the meshing. So that's just something that we try and provide as many tools as we can that are helpful. But if you say need to work on a workflow that uses our software to prepare the model and then bring that to another program before your FEA solver, that's something that we also support. So yeah, it's going to fail. So let me. Yeah, you can see all these triangulation issues here. I'm going to redo it, and maybe I'll just do it with this. So I'm going to create a volume mesh, and it failed again. So I'm going to it really doesn't like me today. I just did this, and that's the fun part of prepping these models for finite element analysis. Is it's quite picky, and I've learned that I've learned with working with some of my groups that if you're not careful at the beginning, you're going to run into problems downstream, and you waste a lot more time if you do it that way, because they'll start running their simulation, they'll run into an issue, and then have to go all the way back. So they waste all the time sitting there before it fails. So it is something that can get quite time consuming to try and to get these ready to go. But I do think spending the time is worth it. So let me try this again. I had some triangulation issues. Nope, it still doesn't like me. So
I have worked with AFM. So when you work with AFM, you can basically work with anything. You need a patient to set up the machine for 6 hours and then do a test. Maybe it doesn't work. Next day, doesn't work.
yeah, it can be quite tedious. And even right here, all I'm trying to do is create a volume mesh, and there's something going on with this part that is not super happy. But I'm trying to get there. If it doesn't work,
yeah, it's a real
we'll see. Did it already fail? That's exciting. So last ditch effort, I'll go to mimics. So I just copy and pasted. So right now I just have this single surface mesh. What we'll see, maybe I'll just try and create a voxel mesh. This is just going to use my segmentation. And then once I have a voxel mesh, it's going to be the same as like a volume mesh. I don't like to do it this way. I like the control that you have in 3-matic. But I can create one here, and then I should be able to kind of walk you through the material assignment of like how we go about doing that, as long as I don't. It's the end of the day for me, so I can think my computer's ready to go to bed.
Your child was calling you, yes. I guess he was calling you.
No, he got quiet again, so he's okay. We'll see. It might be a lot of data.
This is quite normal, for the finite element, even having such software to prepare that, as you mentioned, you can encounter many errors afterwards if you don't fix things.
Yeah, even doing the prep work, as you can see, you can run into a lot of issues. And yeah, it's complexity of the structure is a big thing that will come into play. If you're doing a simple long bone, we don't tend to, I mean, you don't tend to see so many issues. But yeah, once you start getting to these complex structures, then that's where you'll get these weird intersecting triangles, overlapping triangles that you kind of have to deal with. Whereas like a femur, you're not necessarily going to run into that issue. But it created, so you can see now I have this voxel mesh. For material assignment, I'm not going to really go into too much. We do have different methods of doing that here. So gray value based, what this is going to allow you to do is basically take the intensity values. So in this case, it's a Hounsfield unit scale. Take that intensity value from the images, basically put it through these different calculations to get, say, your density, your Young's modulus, your Poisson's coefficient based on each individual voxel. So that's the gray value. So if you know, and I don't have anything for soft tissue, but I know in the help guide of mimics, we've gone through literature and kind of put together tables for hard tissues like bone, cortical bone, spongy bone. We do have some values there, but that was just taken from literature that's out there. Those density values, the Young's modulus, you basically would just be able to go in, enter that, and it would basically take your intensity value, put it into here, and then assign the material properties to individual voxels. So I mean, I could hit apply here, and it's really just all you're going to see in this case is basically one material for the blood, and then you'll see another one for the calcifications. So it's really just looking at the intensity value. So those calcifications tend to be brighter in these CT scans. So you can kind of see there's some calcifications at that valve level. Yeah, this is, I mean, the basic. So this is just one material type. You can have multiple material types, and then basically spread out. So material one, maybe you want that to be a certain type of tissue. Material two, a different range of tissues. So there's a lot of flexibility with the gray value based assignment. We have mask based. I don't typically see a lot of people using that, but it's a similar situation where you would basically put in number of materials, your density, your Young's modulus equations, Poisson's coefficient, and then homogeneous is another one, to where if you just want to assign a single material value, you can do it this way. I think the only time I really see people using this is like if you're doing an implant and you know what material the implant's made out of, you can import that information here. So it's helpful. I just don't see it as frequently. I'd say the gray value based is the more frequent option that you can assign here. And this is, again, it's going to be a static, because your image is static. It's just going to be a static assignment of that material property at the voxel level at that time. So yeah, nothing's moving really. Yeah, it's just at this time. And then for export, if you wanted to include, say, these material properties, you would need to export a mesh. So we have a couple different options. So if you wanted, say, ANSYS, we can go export to ANSYS. We have our part, we have our mesh, and then we have materials. If you export your mesh, you would just pick where you wanted to export it to, your output file. So whether it's an INP, a mesh file for Fluent. So we do have a lot of options for this export, but I would basically just take this once I've done everything, hit add, and then OK. And then what I will do, I should be able to open that file. But then, yeah, once you export that, you would be able to say bring it into ANSYS, and that all that material property assignment should be included.
And ANSYS being one of those finite elements.
Yeah, one of them, yeah. Yeah, I think I might have broke my
People
computer.
use ANSYS a lot in bio. The Abacus I've worked with or heard that.
Yeah, so I do have a lot of groups that are starting to use ANSYS. I think they're starting to focus a little bit more in the healthcare sector.
Okay, good.
One of my colleagues is actually he's leaving to go to ANSYS and work on the healthcare side of things. So it is something that I think they're starting to put a little bit more interest into. Um, but yeah, we have Abacus as well. That's an export option as well. But say you don't like how this assigns material properties. You have a program that can do all your meshing. We do just have like the normal 3D object file exports, whether it's an STL, an OBJ, 3MF. So for different applications, we do have
Yeah.
basically any export that you might need to work in your workflow.
Mhm. Nice.
Are there any questions? I know I went really quick and then I ran into some fun problems.
No, I think yeah, I think that was good. So I guess we could see the whole thing. And there is another question from around. Maybe other students might have other questions. Yeah, we have about maybe 5 minutes. Yeah, go ahead, please.
Real quick, what is a grow? How do you grow an area? Because I saw for the left ventricle, you did that. What does another area do?
So the region grow, is that what you're asking about?
That you're growing the region?
Yeah, so that region grow, so I think this is what I'm talking, this tool here. I think that's what you might be referring to. So what that's going to basically do is allow me to place a seed point in the structure. And then basically from that seed point, it grows out voxel by voxel until it hits an edge. And then anything that's not connected to the set of voxels that it basically grew to, it will get removed. So typically any floating voxels, this will get rid of that. So if you have a noisy scan, so say you're using like a heart kernel scan for like a bone, and when you're segmenting your bone, you may have a lot of speckle in your scan. So doing a region grow on the bone can get rid of a lot of that noise that you might be seeing.
And can you do it on the outside? Like if you did like, let's say you chose specific counts per units where you got the right isolation inside, but you got all this noise on the outside. Can you do the grow to get rid of the outside noise?
Uh, if it's connected, that wouldn't get rid of it. If it's not connected, so basically if it's like floating on the outside, that would get removed. If it's stuck on the external surface, one thing you could try in 3matic is we have this remove spikes tool. So this is pretty good at removing, say, external noise that may be on the surface that might not actually be there. So you might, if I zoomed in, you might see like little like pyramids sticking off. This remove spike tool at the 3D level is quite helpful. We do have a smooth mask tool in Mimics that could also potentially get rid of some of that noise on the external surface. Well, it would basically do it to the whole mask. But yeah, typically if it's an external thing, that's where you would see it. But yeah, if it's not connected, region grow would definitely get rid of it.
Thank you.
Yep.
Any other question? Yes.
So after you get your 3D mask, what are you like gonna do with it? Are you gonna have it 3D printed or are you gonna keep it in simulation? Or does it depend on the part that you're looking at?
Can you repeat that? It's a little quiet. I don't know how far away you are from the
Yeah,
computer.
so she's basically asking what would be the next step? Would it be 3D printing? Would it be what was that?
It will be on a simulation.
Simulation, finite element. I think yeah, he's asking what could be the next steps, for example, for the one that you showed us.
Yeah, so next steps, I mean, yeah, it really depends on what the application is. You could export these 3D objects as an STL, send it directly to a 3D printer if you were trying to print a 3D model. If you're trying to go to FEA or CFD, exporting it in the correct file format from here if you do the meshing in Mimics and 3matic, or if say your CFD solver has some meshing tools to basically assign boundary conditions and all that fun stuff. We can just export it as a 3D object from here, most of those programs, I believe, can import like STLs. So yeah, if you're going to VR, there's certain formats that work well, like OBJ, so that will retain surface color. So if you're more interested in having different surfaces colored different ways, you could export it there and then use that for different applications. So yeah, I mean, it's kind of open-ended once you get that 3D model, what you want to do with it.
Excellent.
I think earlier you mentioned that the Mimic software is an AI-based program that's trained in-house. For that in-house training, what does that entail? Is it like people doing this job manually and then the AI trains on them, or is it by some other means?
So with the AI algorithms that we do have, so not everything in Mimics is AI based, but we do have some segmentation, like that CT heart tool I showed, that's AI based. So basically what that was done in-house is basically we have a repository of scans that we have segmented. Basically use all that segmented data to train an algorithm, and then once you have the algorithm trained, you basically want to validate that it's meeting the gold standard. So we've developed a couple tools that are already in here to get to that point. So if you wanted to see like the dice coefficient of what the output is, we have this compare mask tool. So that's kind of the process. So yeah, everything's segmented, exported in the correct format. Then they go through and they train the algorithm. And then from there, once they validate that the algorithm is segmenting the way they want it to, and then it's really just deployment. So in this case, they programmed that algorithm into that CT heart tool. We have some groups that are doing this themselves. So like some bigger hospitals that have a ton of data that they've already segmented. They have some engineers in-house that will go through the process of training an algorithm to do the segmentation for their high case volume anatomies. And then with that scripting module, they can actually basically call that AI algorithm they can basically run a script to import the images, call that algorithm to do the segmentation, and then automate their workflow that way. But in-house, yeah, it's the data that we have already segmented that's used for the training.
Very interesting.
Excellent. I've also heard that your software has many tools, can have additional toolboxes. Maybe the heart one that you showed could be one. Is that an additional toolbox?
Yeah. So everything's based off the base module. So the base module is going to have your basic segmentation tools, your basic measurement tools, some post-processing for like the 3D models, like the wrapping and the smoothing, the fixing. But then yeah, we do have different modules, so it's a modular-based software. So once you have that base, you can add modules on that fit your workflow. So say that group that maybe wants a hollow heart, maybe they need to add the design module, because then that gives them a little bit more of the design capabilities, whether that's hollowing, cutting, designing primitives, magnet. So some groups are printing models that they cut, and then when they print it, they want to have holes on the model to where they can glue magnets in, and then they can basically have a model that's complete, but then they can open it with magnets. Maybe the design module is helpful for them. We have that FEA module that I believe is in your evaluation, that has that meshing capability. So the surface mesh, the volume mesh, assigning materials. We have analysis. So if you wanted to say fit a center line to this aorta and take, so if I go to my measure menu and take measurements based off that center line, so being able to say, look at the cross-sectional area at a certain point along this vessel. Yeah, so there's a lot of different tools, or a lot of different modules that can be added on. Not everybody needs everything, so that's kind of why it's developed that way.
Excellent. Very good. So maybe the last question. Yeah. Oh, go ahead.
No, because
That's that?
Yeah.
Okay, yeah, I guess we would have more. Yeah, go ahead.
So, with this kind of application of 3D printing a model of the patient, so the surgeon can practice on it. How do you protect against like any medical liability or lawsuits that could arise from the software not giving the right dimensions of like a person's anatomy or something like that?
So are you talking about like the regulations with using this technology for printing? Yeah, so right now, that is something the FDA is looking into. So at the point of care, they don't currently really regulate any of this. They're working on it. They have given a lot of guidance for hospitals on how they want to approach it. But with that being said, we do have a medically cleared um, version of the software that's gone through the 510(k) process for clinical use. So with trained users, they can basically take their CT, their MRI, their 3D echo, go through, use that medically cleared software, and then if they're going to say a 3D printed model, we've gone through the process of validating um, basically the accuracy of certain printers and materials. So with that clearance, it basically would then allow you to create the virtual model that can be used for diagnostic use. But then if it's printed on a certain printer with a certain material, that physical replica would also be cleared for diagnostic use. So it's a lot of work on our end that we've done more on the medical or like the hospital side with that FDA clearance. But the hospital itself, yeah, a lot of people will say it's practice of medicine. I think that's going to change at some point to where the FDA treats a lot of these point of care 3D printing labs as medical device manufacturers, where they have to have their own quality management system in-house and be audited and stuff like that. So on our end, we've gone through the clearance process to help them out. But I think it's a lot of work on their end as well to make sure that yeah, what they're creating, what they're using for clinical use is safe and effective.
Thank you.
Okay, very good. Yeah, thank you so much, Alex. It was very useful, very helpful, and gave us an idea about the software and also how the whole process would work. So I appreciate you, and let me ask the audience. So please join me to thank the speaker. Thank you so much. Is there anything else that you want to add? Please do. Or otherwise, I know that your baby was calling you.
Yeah, nothing on my end, but if you do have questions on the software during the evaluation, feel free to reach out.
Sure.
I can help out.
Okay, sure. Thank you so much.
Yeah, no
Excellent.
problem.
Have a good night. Take
Thanks,
care.
you too. Bye.
Bye. Okay. So thanks for the online, Manuel and Brad.